Ceux qui viennent d'arriver, un grand bienvenue dans ce webinaire Focus Technique. On va parler de simulation, de out of distribution, et ça c'est pour les problématiques d'apprentissage. Et juste avant la présentation par Raoul, que je laisserai se présenter, nous avons la chance d'avoir Nicolas avec nous, donc qui voudrait vous passer un petit mot. Nicolas.
Oui, bonjour à toutes et à tous. J'espère que vous me voyez et que vous m'entendez bien. Donc, je suis Nicolas Vialet, je suis directeur opérationnel d'ANITI. Je voulais profiter de ce premier focus technique de l'année pour vous adresser au nom de toutes les équipes ANITI nos meilleurs vœux pour cette nouvelle année et vous remercier d'être nombreuses et nombreux à ces focus techniques. Vous savez que c'est un dispositif qu'on a lancé il y a à peu près un an maintenant, qui vise à faire mieux connaître les résultats de notre recherche auprès d'utilisateurs potentiels que vous êtes, et quelque part à faire le pont et le lien entre le monde économique, le monde des entreprises et le monde de la recherche. C'est un des objectifs qu'on poursuit. Donc, ce dispositif, on le fait pour vous. N'hésitez pas à nous faire des retours sur ce que vous trouvez bien, perfectible, améliorable, et ce que vous pensez de devoir faire évoluer. On s'en servira pour améliorer les choses dans une année qui est un petit peu particulière pour nous, puisque 2023, pour ANITI, c'est la fin de la phase expérimentale qui avait été voulue par l'État, et on se prépare à une phase beaucoup plus pérenne qui débutera début d'année prochaine. Et on est en pleine préparation, donc c'est le moment pour vous de nous nourrir avec vos retours d'expérience. C'est également le moment pour vous d'exprimer les axes de recherche que vous souhaiteriez que l'on poursuive pour servir à vos applications. Donc, merci encore d'être là. Je remercie également tous les organisateurs et tous les chercheurs qui jouent ce jeu-là de présenter, de se mettre dans un format qui vous permet de voir autant que possible comment utiliser nos résultats de recherche. Et je vous souhaite un excellent focus technique. Profitez-en bien, apprenez beaucoup de choses et n'hésitez pas à revenir vers Raoul ou vers François-Marie si nécessaire.
Merci, merci Nicolas. Raoul, the floor is yours.
Ok. Donc, je vais me présenter d'avance. Je suis un doctorant au LAS, CNRS. En fait, déjà au dernier mois, j'espère, pour finir la thèse. Et ces travaux de recherche, ça c'est une partie de travaux de recherche qu'on a fait pendant ces années là-bas au LAS, au CNRS. Et c'est avec une collaboration spéciale de ANITI. Donc, par exemple, c'est Joris Guérin qui a participé de ces travaux. Donc, on a fait cette collaboration et après, bon, ça a bien progressé finalement et on a eu l'opportunité de publier ces travaux aussi dans une conf aussi de safety. Mais bon, et aujourd'hui, je travaille chez Continental dans le groupe de intelligence artificielle là-bas et focusé sur les voitures, sur les systèmes autonomes. Et voilà. Et maintenant, si on peut, je peux commencer alors à la présentation. Juste une note, je veux présenter en anglais parce que les slides sont déjà en anglais et j'ai fait la présentation aussi dans la conférence en anglais. Donc, je pense que peut-être ça va être plus fluide si je le présente en anglais, si c'est pas un problème. Mais de toute façon, vous pouvez après poser les questions en français sans aucun problème. Bon, je vais switcher alors pour la présentation. J'imagine que vous pouvez regarder mon écran, le titre de la présentation en plein écran, n'est-ce pas?
Oui, c'est bon.
OK. Donc, je fais un switch là aussi pour la langue. OK. Donc, so this presentation, it's called SiMOOD, because this makes some reference to the simulation that I will show how we perform this simulation. And this is evolutionary testing simulation of out of the distribution images. And I will explain better what is this out of distribution. But the main intention of this presentation will not be just me talking about the architecture or the solution that was presented in the conference, but also take some part of that in the end, also to show the repository and some important information or some important guidance to someone that wants to use this tool and perform some experiments by themselves, and to use that. I developed this this tool. We developed this tool to work with Carla Simulator. I don't know if everybody knows about Carla Simulator, but I will give an introduction to. And yeah, let's start. And of course, as I mentioned, it was with ANITI and Joris Guérin, Jérémy Guilochet, and Hélène Weislang. Jérémy and Hélène are both from LAS, and Joris also, but Joris is also from ANITI. Okay, so as I mentioned before, this talk is divided into two parts. We have the scientific context, because if I go directly to the code, it will be weird without the context and without showing to you how is this architecture of the solution and so on. And after that, I will show the repository with some instructions to run into Carla Simulator, or if you want just to use the solution separated from Carla, you can also use it. So just to give some introduction, for example, here, let me just take this window here. 1 minute. Okay, perfect. So just to give an introduction, why we develop such things, because especially in computer vision tasks, these computer vision tasks nowadays they become increasingly used and applied in the cybercritical systems, and especially in the industry too. But we still have a problem when we talk about safety. When you say that, okay, I have a machine learning model with 99% of accuracy, which is great actually, but when we are talking about the safety aspect, it means that yeah, there's 1% of the time that the model will give a wrong output. Depending on the application, it's not a problem. For example, if we talk about recommender systems for something like Netflix, for example, or Amazon. So if it recommends to you 3 moves in the end, when you watch a move, and in the end you have these 3 options below to choose if you want to pursue and to continue to watch movies, and if you one of these 3 moves, these 3 recommendations, it's not good and it's not fits for you, it's not a problem. But if we are talking about cybercritical systems like autonomous vehicles, this is a problem, because it means that a false negative for the object detection means that the vehicle didn't see, for example, a pedestrian, and it came in, and it may lead to hazardous situations. So it's very important. And so this is why I put this line here, that we still have this issue that even with deep learning, we have wrong predictions at runtime, even when the neural network says that, hey, I'm 100% sure that's I don't know, that's an object A, but actually it's not the object A. And looking at this dependability angle, we have several solutions that are normally are applied for traditional systems, not these ones that includes machine learning. And one of them is called safety monitor. So the safety monitor is, imagine like a redundant system that you put together with the machine learning, or together with the system that you want to perform the monitoring. And this redundant system will look at something, some source of information, and say, hey, I don't agree with this, with the output of the system that I'm monitoring. So if I don't agree, I will trigger some safe mechanism. It can be triggering another system, or degrading the functionality of the system to something more restrict but safe, or even just stopping the car, for example, if we can say. And when we are talking about computer vision tasks, so we are talking about images. So in this case, we have several specific problems that can happen when you are working, when your system is running in a computer vision task. And these issues that can happen at runtime is called out of distribution. Actually, it can happen with any machine learning model, even the ones that are not from computer vision. But for computer vision, we have specific problems that I will show next. And out of distribution means that really something natural. When you train your machine learning, you train with your data, and you have this assumption that your data is representative of the data that your system will face at runtime. But if it changes a little bit at runtime, sometimes the model can generalize very well, sometimes not. So which are these examples that may lead to some problems to detect, to the machine learning model detect correctly class in an image? So we have at least these 5 types of OOD that I'm calling here. So we have noise, like Gaussian noise, or some problems in the sensors, for example. We have distributional shifts. It means that, for example, you train your model with images during the day, but now your system is running in a vehicle, for example, and now it's night, for example. We have novelty classes. This is straightforward because we trained with to identify cars and trucks, and in front of the vehicle, we have something like a bike or a person. We have anomalies. These are more regarding some problems directly on the sensors, not exactly in the environment. And we have adversarial inputs, that it means that someone is trying to fool the machine learning model, such as some examples that we have in real world examples, like putting some stickers over a traffic sign to make the model think that this traffic sign is something different than what is in fact. So this safety monitor that we propose, that is generally proposed to monitor the machine learning model, works simple like that. You are seeing here in the left, that is, we will have the components that you want to inspect, that you want to monitor, and you have the information that this black box uses. For example, in this case here, on this example, you have 3 types of observation. You can observe the image, you can observe the neurons, the neural activations of the machine learning model, or other internals, and you can look at the predictions and confidence values too. Okay, but we have the problem that first to do that is as you can imagine, it's not easy. It's very difficult. So it's a research field by itself. And you have the other problem is, okay, once that I have a system, I have a safety monitor to monitor the machine learning model, the intelligent system. How can I test that? And how can I generate data to test that? Because this is the main problem normally when we talk about validating industrial systems, for example, the corner case. So how can we find the corner case without exploring everything that we could or that we would explore? How can we do that in a smart way? So this problem is very big because when we are talking about pixels, about image, so we have the dimension of the pixels. It means that if you take, imagine just an image like 200 by 200 pixels, that's quite small, right? But in this case, you have to multiply 200 by 200, and you have this in 3 dimensions, RGB. So you have to multiply it by in cube. So you have a very big space. And knowing that if you change some pixels or some blocks of pixels, you can make the machine learning give a wrong output. So how can we test this machine learning models, these object detectors, and the safety monitor, knowing that this space is very big? So in this case, we thought about this architecture here that I'm showing to you. So first we have a generation, we have an evaluation, a simulation and evaluation. So what it means, that this is what I called this evolutionary approach. So we deal with that, with the problem, like we do with some problems that we use that we apply genetic algorithms, for example. So imagine that we have this pool of genes. Pool of genes means that is all the transformations that you want to test in your simulation. It means all the transformations that you want to perform on the image that will be fed to the machine learning model. So for example, imagine that you wanted to simulate rain. So you take the image during the simulation and you apply an effect, a rain effect, for example. So you can imagine that you have several levels of rain, and you can have several levels, for example, of noise. So it's quite big. And okay, but you imagine that you know a priori which are the transformations and the intensity that you want to test. You just know that you cannot test everything, but you know what you want to test. And these are the pool of genes. And in the beginning, the algorithm just takes this randomly from the space of possible transformations and intensities. And the genetic algorithm will find or will search just the n best transformations that may lead the machine learning model to fail, because the main goal here is to know when the machine learning fails, because we know that this object detector has a good accuracy, but we know that we cannot rely 100% of the time on it. So we want to find the corner case. We want to find the examples that makes our machine learning fail. But of course, realistic examples. I cannot put a transformation like black image and expect that, okay, now I'm finding something useful that actually is not, but something like the minimal perturbation on the image that makes the machine learning model give a wrong answer. So this is the main goal. It is so this transformation is applied at real time in a Carla simulator, and after that we have the answers regarding the hazards, if the model didn't see a pedestrian, or if the car, for example, if the system stopped, if the car stopped thinking that there's a pedestrian, but actually there's nobody. I will explain the example afterwards. But this is the main schema. So mainly it generates the initial population with the pool of genes. It means it generates, for example, haze with intensity 2, and rain with intensity 3, Gaussian noise with intensity 4, for example. And after that, we apply these perturbations, this pair of perturbations and the intensity, to the training set, the same training set that is used to train the machine learning model. And we evaluate the answer of the machine learning over this new transformed image. This step here, it's offline. So it means that you perform this offline, and after that it will output a fitness score that's based, for example, in the accuracy of the machine learning model over this transformed image. And you select using the classic selection parts of crossover and mutation. For example, you just take the transformations, the best transformations, and you exchange the transformation between the pair of best transformations, for example, the crossover, and in the end you take the best ones and update the population. In our case, we can take, for example, the 2 best transformations and put in the place of the worst ones. And what is best? Best is the minimal perturbation that makes the machine learning give the worst results. So we are not interested as well. We are not interested on finding perturbations like noise in the max level of intensity, because of course we understand this is quite more easy to find, right? Because we just need to put at the max level, but we want to find also the subtle modifications, subtle transformations or perturbations on the image that makes the machine learning give the wrong prediction. So here I just put some values regarding the parameters that we tested in our genetic algorithm. So we tested, for example, with 10 generations. It means that this loop here is done 10 times. We test with 20 generations, 30, 50, and we test with a population size of 10. It means that is 10 transformations, the best 10 transformations. After that, the 20 best transformations, the 30 best transformations, the 50 best transformations. And this number here that you are seeing are the number of hazards ordered by generation by population size. So as you can imagine, we have a big space of transformations, but we are able to take just 10 or 20 ones, and this can also show us some interesting results. So it like that. For example, if you look at this image in the sub-image A, we have an example of novelty class. So this is quite straightforward. So with this tool, you can add any other image that you want in your simulation, and it will put this image inside of the simulation. These are not the I did not save the image to make this transformation. This is happening at runtime, at the same in simulation time. So this is made at simulation time at Carla, and you can choose the image that you want to. You just need to use PNG because you have this transparency if you want to be more realistic. And this will do the scale to you automatically. If it's far, it will be smaller, and when it's more close, it becomes more bigger. And you have this example, subfigure B. Just to give a context here, this system, this case study here, it's about ADAS. So in this case, the objective of the system is a vehicle that is going through the street. You have these static objects in the right side, and the bounding box, even that bounding box is touching this region that you see here. This region actually are a safe region. It means that if an object enters in this region, the car has to stop. But it doesn't have to stop when there is a static object like a car that's touching the area. So the semantic information is important here. It's not just about a sensor that detects that there's objects, if you can understand. So this is why we are using here an object detector, because you have to know the semantic information. Okay, so in this subfigure B, you can see that SiMOOD found a small perturbation that in this case is a condensed water, and the object detector thought that there was a person there. If you see here, he's saying, hey, there's a person, and we'll touch the safety area, so I have to stop the car. So this is an example of false positive that was found during the simulation by the combination of transformations that SiMOOD provided. And in the subfigure C, you can see the opposite. You can see a false negative. You are seeing here in the right, I tried to zoom it. In this right part of the subfigure C, you can see a person here. But the object detector didn't see it because we had a small perturbation using haze in the simulation. It was provided by SiMOOD too. And we have problems too when we combine transformations on the image. For example, if you look at this subfigure A, we have a perturbation like smoke with an intensity of 0.25, okay? And we have, then you can see that the object detector found the object, found the pedestrian there. If you look at subfigure B, we have an effect that's called grid dropout. It's when you have some pixels that goes dead. In this case, with intensity 2, the object detector also was robust enough to find the pedestrian. But this is the interesting part. When you combine both, you can have the problem like the subfigure C, that the object detector doesn't see it. It doesn't work correctly. And the most interesting thing is that you can combine that even with lower intensity of perturbation. So it means that when we combine smoke 0.18, that's less than 0.25, with grid dropout, it was enough to make the machine learning to not see the pedestrian. And it was provided by SiMOOD. And finally, we have other type of hazard too. That is when the order of transformation also matters. So it means that the space is very big. If you are talking about a pair of transformations, it means that they are not commutative, and your optimization algorithm has to deal with that too. So in this case here, if you have grid dropout in the smoke, the object detector sees the pedestrian. But if you have smoke first and grid dropout afterwards, no, it doesn't work. So this can be also tested with this tool. Okay, the problem, of course, you always have problems, advantages and drawbacks. And the drawback of the tool is that since we are performing transformations, image transformations at simulation time, so we need more memory. And in this case, since we are talking about high resolution images, that was the case here, 1280 by 700. In this case, we have this this problem that, okay, we need an extra amount of memory of 2.5 giga, and but SiMOOD can be of course optimized because it's just academic first version of the tool. And we have the overhead too regarding the time. It makes that the simulation, if your simulation takes 1 minute, so you should know that we have a simulation a bit more slow because we are applying constantly these transformations frame by frame. So we have an overhead of 20%. And yeah, here I put some information regarding the installation, but I will go now through this to not spend too much time. And of course, it's in Python. This is why you are seeing here pip install, and we tested with Linux. And yeah, so if you want to use the tool, you can use it for two different purposes. For example, you can use it just to generate, just to find the transformations, the image transformations that may lead the machine learning model to wrong outputs. It doesn't matter the system. It means that if your problem is about image classification for identifying industrial objects in a, I don't know, in a step or something like that, in automatic step, you can use that, for example, as, okay, I want to know if I have some interference on the image, or if you want to just to test, for example, if your system it's about an image classification system regarding a camera that's outside and make some kind of surveillance. So in this case, we can test different environment conditions and also sensor problems with that. So the application is independent of the application, just need to be regarding images, and you just need to provide your data set that you use to train your model. Or if you don't want to find any, if it's not your purpose to find smaller perturbations that leads to errors, if your purpose is more about, I want to perform some specific transformations that I know which they are, and it's quite defined, but I want to perform that in an easy way at Carla. So you can use that you can use the tool just to do that. So you can use the repository just for that. You choose the transformation that you want to apply at Carla at your simulation, and you run Carla, and the perturbation will be done at simulation time. And for we tested with YOLO v6 version 6, and we had at least 16 megabytes of memory. But anyway, for simulation, you need at least 16 megabytes of memory to do it. Okay, and now I will go quickly to have some time for your questions, but I will go quickly in the repository. So let me see if I can, if it's possible for you to see my screen, or if I have to maybe change here. Let me see. Maybe I have to to change the screen. Let me see.
Just to precise during the search for Raoul, and if you have any question, don't hesitate to use the question part, and you can ask your question in English or in French, as you want.
Yes, so I think that now you can see, now you are seeing the repository, right?
Yes, yes, it's okay, Raoul, yes.
Okay, nice. So let me just put it here, the window of the presentation. Yeah, nice. So here's the repository. As you can see, the repository is just that SiMOOD, if you want to take a look later. So Raul Sena Ferreira and SiMOOD. And here we have two parts. So in the README, you have the information to install it in your PC. But to give you some, just a quick guidance, what do you need is first to install Carla simulator in your machine. And after you install Carla, in this case, I tested with 0.9 and the version of Carla, but it will probably work with the other versions that are near from this version too. And if it's not works, you can drop this, you can open an issue here in this repository, and we can take a look together and maybe help the other person that wants to do the same. And the only thing that you need to do is, once that you install Carla, you take this repository here with, you can clone it using git clone, but you can also just download the code, there's no problem. And you put that inside of a folder called Python API. When you install Carla, it will be with this folder. So you just need to take this repository and put inside of this Python API. And once that you put there, you just need to create a virtual environment if you want to, just to not mix the dependencies that will be installed with the dependencies that are already installed in your PC. So you just need to do something like a Python using VM, for example, or if you want to use Conda too, it's up to you. But I would consider using VM because I installed with pip. So inside of this environment, you create a virtual environment, you start this virtual environment, of course, activate it. And once that you do that, you just run in the terminal pip install our requirements .txt. I didn't put here, I have to update. But yeah, you just need to do this pip install. And after that, you just need to provide the egg file. This is also inside of your distribution. Yeah, and after that, maybe you have to set up your Python path to pointing to the Python path that we have in this scenario execute in this part here that I called scenario executor. Why? Because we use a scenario runner. That is a tool for generating scenarios in Carla. So I will enter now in some folders and I will show to you. But yeah, so in this case, is everything that you need to do. And after that, you just need to run Python main.py. That is the main, that is inside here. That is the main script. As you can see here, this is the main script. So yeah, this is the egg file that I mentioned, and this you can download it. It's not a problem for you. And here we already have all the functions that works with a scenario. And if you wanted to change the scenario, it's not a problem. You just need to write the scenario. In our case, we are using Open Scenario. And as you can see here, you just call the scenario that you want to. In my case, was this scenario regarding the vehicle that goes in a street, and we have a pedestrian that crosses the street. And I will show this is actually quite simple. You just need to substitute here with your scenario, and after that it's okay. It's everything that you need. The remaining part, it's already here. It's already implemented. And we have some, of course, we have some arguments, but we don't. If you want to, you don't need to change it, except, for example, if you want to use a different object detector. So I showed to you about YOLO, but I also implemented here a transformer. And you can put any other object detector model here. And for now, we have 30 transformations from these 4 types of OOD data. And you can play with any of them. Yeah, so it means that you can pass it through argument. Okay, and this is the part of the Carla. If you want to run Carla with these transformations that you want to. Okay, and the second part, just to finish. Here you can put the models anyway, and here are the scenarios. And in the end, you have the option to save all the simulation in a structure of images, all the frames in a folder with images. Okay, so if you want afterwards to use it. Okay, and finally, just to show the second part, here in the evolutionary steps that I put here at the README part, is everything here in the README, even the paper too, if you want to look in more details, the paper. And here you have the second part that is about how to make SiMOOD work, to give you some examples of transformation. The same way, you create a virtual environment for that, and you install by pip requirements, and you run just one file that you can modify as you want. This file it contains some parameters for the genetic algorithm that you can change as you want. I went here just to not be incomplete in the explanation. So here are the calling for the functions. As you can see, I'm using here a data set for object detection, COCO data set, but you can just need to change that for your data set. You can use any data set, since this data set has a label and all these things. And here are the parameters of the genetic algorithm, and you can test as you want. Here are the functions that are used as a fitness score. So I'm using map, that is a metric for the object detection. But if your problem is about image classification, you can use precision, you can use recall, and you even can implement yours here, like accuracy or MCC, Matthews coefficient correlation, and so on, or F1. It's up to you. And here you have the pool of genes. It means that all the transformations are here. If you want to know exactly what are the transformations, you can see in the paper, but you can see here too. So you can see that we have several transformations and the range of transformations. If you want to add another one, you can. You just come here, you add the name of the transformation, the range of intensity, and you map this here. And the algorithm will search for you. And finally, if you want to change the number of generations, it's very simple. You can just come here in the same file, main.py, evolutionary steps main.py. You come here and you change directly. I let some examples here commented, but it's up to you. You can use whatever you want as a parameter to play with this functionality. As you can see here, the crossover probability, the mutation probability, the population size. If you want to pass an array of population size to test in different population sizes, you can. So it's quite simple, as you can see. And yeah, I think it's all. And we have at least 10 minutes if you want to make some questions.
Thank you very much, Raoul, for the presentation. Donc nous avons vu pourquoi, comment utiliser et à quoi ça sert. Alors le sujet essentiel, donc c'est les out of distribution. On est en dehors de la distribution. Donc une question posée par Bertrand. Point difficile, comment s'assurer que les individus qui sont générés par l'algorithme, une fois les perturbations faites, enfin avec tout le mécanisme que tu as proposé, soient bien réalistes, c'est-à-dire d'une certaine façon qu'ils soient à l'intérieur du domaine d'emploi ou sur l'ODD, si on veut faire le lien avec l'OD.
Yeah. Oui.
Et si tu préfères, hein, on comprend, mais j'ai posé la question en français.
Ok. Bon, je peux répondre en français, c'est pas grave. Donc, dans ce cas-là, c'est juste les transformations qu'on a choisies. C'était des transformations déjà basées sur la littérature, des benchmarks de image classification. Donc, ces benchmarks, ils ont utilisé aussi des transformations comme celui-là. Et bien sûr, si on choisit un range de transformation qui c'est trop grand, par exemple, si tu appliques beaucoup de Gaussian noise, ça fait que l'image ne soit pas visible, donc c'est pas réaliste. Ou sinon, si tu mettre beaucoup de brouillard, c'est un peu, c'est non réaliste aussi. Donc, qu'est-ce qu'on a fait, c'est que on a testé juste les bordures, juste la frontière de transformation. Donc, ça veut dire qu'on a regardé quels sont les types de transformations qu'on veut. Dans ce cas, on a éliminé pas mal de transformations aussi. Donc, c'est pour ça qu'on est arrivé à la fin à 30 transformations. Et c'est pour ça aussi qu'on n'utilise pas l'adversaire ici. Parce qu'on n'avait pas une étude de cas avec traffic signal et avec les stickers, tout ça, donc on n'avait pas. Et en même temps, il n'y a pas trop de sens d'utiliser adversaire pour changer les pixels de l'image parce que ça présume que tu connais le modèle et que tu as l'accès au modèle aussi. Donc, ça, c'est déjà quelque chose qui c'est pas réaliste et on n'a pas considéré dans l'outil. Donc, juste pour répondre vite à la question, c'est que toute cette liste qu'on est arrivé à la fin, on a regardé la frontière. Ça veut dire la première transformation, c'est la plus légère qui soit pas beaucoup, et qui soit réaliste. Et surtout, à la fin, si la transformation, ça ne rend pas l'image illisible ou quelque chose qui, tu sais, qui sera impossible d'arriver en real time. Mais entre les ranges, ça, on n'a pas regardé bien sûr, mais on assume que ça pourrait arriver, on va dire. Mais par contre, on n'a pas calculé les différentes probabilités que ça peut arriver en runtime. Ça, par contre, on n'a pas fait cette étude-là.
Merci Raoul. Si vous avez d'autres questions, n'hésitez pas. Pour l'instant, il n'y en a pas. J'espère, Bertrand, qu'on a donné une réponse à ta question. Donc, en tout cas, je voudrais remercier Raoul d'avoir pris le temps de présenter ses travaux. Je vous rappelle que ces focus techniques qui visent à proposer des résultats d'ANITI qui sont directement intégrables dans vos propres applications. Hein. Donc, vous avez vu comment utiliser SiMOOD, ben, allez-y. La meilleure façon possible de remercier, attends, je regarde s'il y a une question. Ok. La meilleure façon de remercier Raoul du temps qu'il a pris, c'est lui faire un retour de l'utilisation de SiMOOD. Hein, donc, n'hésitez pas, hein, bien sûr. Là, j'ai une question de Fabio aussi qui vient d'arriver. Donc, si j'ai bien compris, vous avez proposé cette méthode pour trouver les perturbations les plus importantes, donc capables de perturber l'algorithme de détection. Ça a été utilisé pour valider la robustesse de l'algorithme de machine learning. C'est bien ça, voilà. Donc, merci.
Oui, exactement.
Merci pour cette reformulation. Ça fait une bonne synthèse de la présentation de Raoul.
Oui.
Donc, gardons-le. Tiens, je le mettrai dans le compte rendu. En fait, merci Fabio. Alors, il y a une question. Oui, ça, on a encore le temps. Est-ce que vous utilisez aussi le retour d'informations pour améliorer l'entraînement des algorithmes de détection?
Voilà, à la fin, il y a un fichier où on garde le résultat de faux positif, faux négatif, true positif, true négatif, surtout faux positif, faux négatif de ta fonction. Donc, ça dépend de ta fonction, mais de toute façon, on garde à la fin. Et là, il y a aussi la transformation. Donc, tu vas voir dans le repositoire qu'il y a un fichier, il y a un endroit où il y a le résultat, par exemple, Gaussian Noise 2 et le résultat qui s'est donné de Hazard pour ça. Donc là, après, toi, comme spécialiste, tu vas regarder ça et dire, ah, bon, je pense que ça, c'est quelque chose d'important à considérer et je peux entraîner mon machine learning avec ce même niveau de Gaussian noise sur l'image, par exemple.
Merci Raoul pour la réponse. J'espère Fabio que ça répond à ta question. Donc, je continue un peu en termes de conclusion. Les prochains focus techniques traiteront de transport optimal. Donc, l'une des difficultés qu'on rencontre dans le transport optimal, c'est quelque part, ce sont les garanties d'un point de vue mathématique de la transformation. Donc, il y a eu des travaux là-dessus qui ont débouché sur des codes que vous pourrez utiliser, hein, donc qui sont évidemment très utiles pour ces techniques d'optimisation, et un autre qui traitera sur l'échantillonnage de modèles génératifs et en particulier applicable à des jumeaux numériques, donc dans le domaine industriel. Donc voilà, là encore, ce sont des codes que vous pourrez utiliser. Je voudrais remercier donc Raoul. Fabio souhaiterait d'ailleurs continuer, je pense, la discussion avec toi, Raoul. Donc j'imagine que ça ne te pose pas de difficulté.
Oui, donc, non, bien sûr, hein, c'est bienvenu.
Voilà. La réponse est positive. Hein. De toute façon, c'est vraiment l'objectif là, c'est que vous puissiez être en relation directement avec ceux qui présentent pour que vous puissiez utiliser. Notre mission, c'est que les résultats d'ANITI, et de façon générale, l'investissement public dans la recherche soient utilisés dans les différentes sociétés. Donc, allez-y, discutez, profitez-en et tirez-en parti. Je mentionne aussi dans le cadre d'ANITI une présentation des sujets sur la robotique qui aura lieu au LAS, duquel d'ailleurs fait partie Raoul, au LAS, physiquement au LAS le 9 février. Donc regardez dans vos invitations, vous recevrez bientôt l'invitation pour ceux que ça intéresse. Je voudrais donc terminer par remercier Raoul de la présentation,
Merci.
remercier aussi Jennifer qui est à la technique là, qui fait en sorte que tout ça fonctionne bien. Merci aussi à Nicolas d'être venu nous présenter ses bons voeux. Et surtout, merci à vous d'avoir participé. Et encore une fois, si vous en tirez parti et l'utilisez, n'hésitez pas à nous faire des feedbacks. Je vous souhaite une excellente fin d'après-midi et puis au plaisir d'un prochain focus technique. Au revoir.
Merci à tous.